A compass is only useful if you trust both the needle and the map. For years, particle physics thought it had a needle pointing in the wrong direction. A tiny particle called the muon seemed to be wobbling more than our best theory allowed. That looked like the kind of crack physicists dream about, a clean, measurable sign that the standard model was finally failing. But the deeper we looked, the stranger the story became. Because the biggest problem may not be that the muon is misbehaving. It may be that we no longer agree on what normal even means. To see why this matters, you first have to meet the muon. It is a heavier cousin of the electron, with the same electric charge, the same spin, and the same role in the particle family, but with much more mass and a very short life. That extra mass makes it far more sensitive to the quantum activity of empty space. And in modern physics, empty space is never truly empty. It is filled with fluctuations, with virtual particles constantly appearing and disappearing in ways that slightly change how real particles move. Put a muon in a magnetic field, and its spin behaves like a tiny gyroscope. In the simplest version of the story, the magnetic factor called G would be exactly 2. But the universe is not that simple. Quantum effects shift it slightly, and physicists focus on the tiny difference called the anomalous magnetic moment, or g-2. That tiny correction is one of the most demanding tests in all of physics, because it includes contributions from electromagnetism, the weak force, and the strong force. If unknown particles exist and interact with the muon, they can leave a fingerprint in that number. That is why muon g-2 became such a big deal. This was not just another precision measurement, it was a pressure test for the standard model. The muon is much more sensitive than the electron to heavy virtual particles, which makes it a particularly good place to look for new physics. If the measured wobble and the predicted wobble refuse to match, that mismatch could have been the first hard evidence that something important was missing from our picture of nature. The experiment itself was extraordinary. Physicists reused a 50-foot wide superconducting storage ring that had been moved more than 3,000 miles from Brookhaven to Fermilab in one piece. Inside that ring, muons traveled at almost the speed of light, while a precisely controlled magnetic field made their spins precess. The whole point was to measure that precession with absurd precision, to watch how quickly the muon's internal compass rotated and compare it to theory. For a while, the story looked clear. Earlier experimental results from Brookhaven, followed by Fermilab's first major updates in 2021 and 2023, agreed with each other and seemed to sit significantly above the standard model prediction used at the time. That older prediction, formalized in the 2020 Muon g-2 Theory Initiative white paper, relied heavily on a data-driven method. Physicists used measurements of electron-positron collisions that produce hadrons, then fed those cross-sections into a dispersive calculation to estimate the hadronic vacuum polarization, the part of the theory that dominates the uncertainty. With that 2020 benchmark, the result looked explosive. The discrepancy grew into one of the most famous tensions in modern particle physics. This was why so many people talked as if the muon might be opening the door to a hidden layer of reality. New particles, new forces, a real crack in the standard model. Then the ground shifted. The problem was never the clean parts of the theory. Quantum electrodynamics is under astonishing control here. The electroweak contribution is also well understood. The trouble is the strong force, specifically how quarks and gluons inside hadrons affect the vacuum around the muon. That hadronic contribution is difficult because the strong interaction becomes non-perturbative in exactly the energy range that matters. In plain English, it is the part you cannot calculate with easy formulas. For decades, the standard workaround was to lean on real collider data. Measure electron-positron collisions, see how often they turn into hadrons, and use that to reconstruct the hadronic vacuum polarization indirectly. It was not glamorous, but it was the accepted yardstick. Then, Lattice QCD started catching up. Lattice QCD takes space and time, chops them into a discrete grid, and computes the strong interaction numerically from first principles. This is brutally difficult, but it has a huge advantage. It does not need to borrow the key hadronic input from collider data in the same way. In 2021, the BMW collaboration published a lattice result for the leading hadronic vacuum polarization that landed much closer to the experimental muon value than the older data-driven prediction did. If that lattice result was right, the famous anomaly was no longer a clean sign of new physics. It was a sign that the theoretical benchmark itself might have been wrong or incomplete. That was the real twist. The debate stopped being experiment versus standard model and became, which standard model calculation do you trust? That is a much less cinematic headline, but scientifically, it is the deeper problem. Because if two serious methods give meaningfully different answers for the hadronic contribution, then the bottleneck is no longer the measurement. It is our control over the theory. And that is exactly where the field stands now. In 2025, Fermilab released its final result, the most precise measurement ever made of the Muon anomaly. The experimental world average is now extraordinarily sharp. But the updated 2025 Theory Initiative white paper no longer uses a combined, data-driven estimate for the leading hadronic vacuum polarization in the way the 2020 benchmark did. Tensions among the electron-positron datasets, especially after the newer CMD3 result, became too serious to ignore. Instead, the updated recommendation adopted a consolidated Lattice QCD average for that leading hadronic term. With that shift, the standard model prediction moved upward and became consistent with the measured value within uncertainties. That means the old simple storyline is gone. You can no longer honestly say, the Muon proved new physics. At least, not yet. The experimental result is magnificent, but its interpretation now depends on how the hadronic vacuum polarization is handled. If the lattice-based picture is basically right, then the famous anomaly largely fades. If the dispersive approach eventually stabilizes around the older, lower value, the tension could come roaring back. Right now, the Muon is not delivering a clean verdict. It is forcing theorists to confront a disagreement in one of the hardest parts of precision physics. And that is why this is still fascinating. The mystery did not disappear. It changed shape. We are no longer staring at a single flashing sign that says, new particle here. We are staring at a conflict between very different ways of extracting one crucial piece of the standard model. One route leans on collider data and dispersion relations. Another leans on supercomputers and first principles lattice calculations. Both are serious. Both are difficult. And for the moment, they do not lead to the same clean story. There is also no instant tiebreaker. The J-PARC Muon g-2 effort is pursuing an independent measurement using a very different technique, but that is a future cross-check, not a finished answer. At CERN, the MUonE experiment is trying another route to the hadronic vacuum polarization itself, using muon electron scattering rather than the traditional electron-positron to hadrons input. In other words, the field is now attacking the problem from multiple directions because everyone understands what is at stake. And the stakes are bigger than one decimal place. Muon g-2 has become a test of whether precision physics can still expose cracks in the standard model when direct searches have not found new particles. If the theory side tightens up and the agreement survives, that tells us the standard model is once again more resilient than many hoped. If the competing methods converge in the other direction, the Muon could return as one of the strongest hints of physics beyond it. Either outcome matters. So the honest version of the Muon story in 2026 is not that the revolution arrived and then vanished. It is that the clean anomaly dissolved into something more subtle and, in some ways, more unsettling. We built one of the most precise experiments in the history of particle physics, and it worked. The Muon needle is being measured better than ever. The real uncertainty is the map. That may sound less dramatic than, we found a new force. It is not. Because when your experiment becomes more precise than your consensus theory, you learn something uncomfortable. Nature is not obligated to reveal whether the problem is in the particle, the calculation, or the assumptions connecting them. The Muon has not settled the argument. It has made the argument impossible to ignore. And that is what makes it one of the best unsolved stories in physics right now. Not because it already broke the standard model, but because it pushed precision science to the point where even our best methods no longer line up cleanly.